And we can start. Hope you're all good. Rested a little rest through the break. And now, this will be our fourth and last lecture about the improper integrals. And moreover, about integrals, generally speaking, 11 lectures about integrals is enough. Next week, we move on to a different subject. Of course, we will meet integrals from time to time, but not as the main subject. And what I want to start with today is the following theorem. I call it the integral test. I don't need to remind you anything specific, so just write it down. Now, as we've already seen along the way, there are many similarities between integrals, improper integrals, especially the improper integrals of the first type on the infinite segment, and series. I mean, the tests are basically called the same, comparison test and series play that we saw last Sunday, and they say the same thing, just phrased differently. This is one for a series, this one for integrals. The integrals of 1 above x to the power of p converges if and only if p is greater than 1. So it was not very, it is similar. Now, the integral test, this theorem states formally a connection between a series and an integral. And it does it in the following way. Let f be decreasing. And if decreasing, that's right. That's right, decreasing? Yeah. Sorry. Let it be decreasing, and if it's increasing, it's just the minus of a decreasing one, so it's not very important. A decreasing function in a segment uh, to infinity. Um, as we proved, or at least mentioned in lecture number 5, 5 was 4? I think it was 5. Decreasing function or increasing by a monotone function is integrable, so we are very good, theoretically speaking. And what I want to say is that the integral of f, you know what? Let's add another condition. No, don't want it to. So the integral of f from a to infinity converges if and only if the series from a to infinity of fn converges. For example, fx, number you like, any number, 45 is a decreasing function in 1 to infinity, then its integral is converges if and only if the corresponding series, which is series of 1 above n to the power of 45, converges. Now, we know that both of the things, the integral converges and the series converges, are true, but not because of our theorem. We know that integral converges. We saw it last Sunday. We proved it for every p greater than 1, and integral converges. And the series is from our last course. As far as I know, Erez and the way he does things, he probably proved it with condensation theorem of Cauchy. But, or not, maybe that's not the right word, but there are um, places, curses, whatever, that study calculus, study infi in a different way. I mean, if you go and study the calculus of the engineers, yeah, not all of them, but the electrician and not the software engineer, which is basically the same as the computer science, but the electrician engineers and such that they first of all they start with sequences, just like us, but then they move to functions without series, which is not logical or correct, but it is probably it makes sense. I mean, how do we define the basic notion of a limit of a function? How Erez does it, how I do it when I teach in Phi1, with limit of sequences. The fx goes to L if every sequence xn, blah, blah, blah. And then in the second course, in the second calculus, infi, fedwa, whatever, they study about series. Okay, moreover, there are places I teach in the, I told you before, Michal Leminal, Rishon LeZion. It's actually my main workplace. And there they start with functions. And only in the second course they talk about series, sequences, and then series. So when one studies integrals before he studies series, the integral test is useful and important. Because if you think about it for a second, it is easier to talk about integrals than to talk about series. What I mean, we started this course 5 whatever weeks ago, and we said, oh no, integrals are very hard because we compared integrals to derivatives. And the derivative is something that is pretty easy not right, but we know how to do it. Whatever the function is, I give you the differentiable function, you know how to find its derivative. When it comes to integrals, we spent 3 lectures and 2 practices about how to find the derivative, and then another 4 or 5 4 lectures about the definite integral. It's definitely more complicated to calculate an integral, be it an indefinite one, or definite one. But yet again, it is difficult compared to finding a derivative. And one must say, note, it's not a fair comparison. Because in order to have a derivative, a function needs to be differentiable, which is an exclusive club, let's say so. Yeah. Every differentiable function is continuous, and there are continuous functions that are not differentiable. And every continuous function, as we proved or just stated in lecture number 5, is integrable. And not every integrable function is continuous. So the club of differentiable function has much stricter conditions, yes, policy of entering the club. So it's not surprising that the functions inside the club of differentiable functions are nice. Um, Comparing to integrable functions. But when we compare integrals and series, here the integrals are the easier part of the equation. Yes, of course, we cannot find the derivative, we cannot calculate any integral around. But what is easier? Finding an antiderivative and calculating a definite integral, or calculating the sum of series? As far as I know, what we are teaching here in Infi1 about finding the sum of series, not just saying that it converges, finding to what it converges, actually, we know to do it when it comes to telescope series, specifically the geometric series, and basically that's it. We don't know how to calculate integrals. I mean, if I told you, okay, let's calculate the sum of arctangents n above n squared plus 1, the hell it is. Yeah? But if I talk about the integral of arctangent x above x squared plus 1, that was our first example, as far as I remember. What was the 5 weeks ago for calculating finding the derivative using substitution. So calculating integral is easier than calculating the series. Meaning that if we study integrals before we study series, the integral test that connects between both of them is a useful and important tool using our knowledge about integrals to know new things about series. But here we study it in a different way. We first study sequences and series, and just then, here in the second course, we talk about integrals. So the integrals test, generally speaking, to us is less useful. Not saying it's not useful at all, but if you enter integral test, Google or GPT or whatever, and ask them for examples, most, if not all, the examples you see are examples when we use our knowledge about integrals to understand something about series and not vice versa. So, by the way we teach and you study in here, the integral test is not very useful, but A, it gives us explicitly, formally, a connection between series and integrals, what was uh, in the air tonight for the last 3 lectures. So it is important just by this point. Secondly, I'm the lecturer. It's my job to write the final exam. And I think that I can use my imagination and find a question where an exercise where you need to use an integral test in the way, to understand the series from to understand integrals from series. That's my problem. And thirdly, I want to discuss it a bit furthermore what the test does say and says what it does not say. Before the test itself, it's not a big chidush in Hebrew say. It'll give us some uh, new information. Yeah. So, or not a lot of new information. So that's why I denied it to our last lecture about improper integrals. Uh, could use it for integrals like the series. Here's the test. In lecture number 8. But it's probably better here. Okay, so this is the integral test. F should be positive in order to have some converging integral, but it's not very important. In phrasing the theorem, one can add that f is a non-negative function, decreasing one. But it's not extremely important to what I want to say. What I want to say, what I want to add here is two things. Let's write what I said, but let's try to make it quick. Um, it is easier to calculate integrals than to calculate than with A, of course. Calculating series, the sum of series. So usually we use this theorem to understand something new about series using our knowledge about integrals. And here we've already studied the series very well. in our last course was probably not that important. Now, I don't want to prove the theorem. I want to give you a sketch of the proof. The proof. Geometrically speaking. Then I want to say what the theorem does not say, and then we can move on. Okay. Sketch of the proof. Let's write it down geometrically. Um, x-axis. Let's say that we have the point A here, and the function f is decreasing. Okay. So with black, I draw the graph of the function f. Now one can look at the points of the series fa plus 1, fa plus 2, only the integers in the series. Let's draw it with a different color. No, we can do it same black on the x-axis. Don't look for the right proportions or something like that. You will not find any. Trying to understand the principle, not to draw something perfectly good. The different color, let's choose something. Now, if we look at the points on the graph itself, we know their heights. They're on the graph. So here it is fa plus 1, it's the level of a plus 1, and here it is the level of a plus 2, and so on and so on. Now, on one hand, one can write down the following rectangles. Notice that.
I think
Yeah.
I think you're doing exactly what we did in data structures yesterday.
And do you study data structures or data structures?
Data structure.
I don't know. I'm asking.
What is data or data? Data. Data. Yeah. So yeah, what we did yesterday is that when it's monotonically decreasing, you can do like a plus 1, a plus 2, or if you move it to the left one, it's under the graph, and if you move it to the right one, it's over the graph.
Yeah.
That's what you're talking about? Okay.
Yes, it is. How is that connected to
Because
data structures?
what was he talking about hashing? Yeah, in terms of uh frame of the hash. Okay. Yeah. I forget exactly why he brought up the because I can look it up. But yeah, basically he talked about this a bit, but he didn't go very deep into it.
Okay, so I'm not going to go deep into it, right? But let's talk about it. Hopefully let's elaborate more. So now we have these rectangles. Every base is of a length 1. And the height is the values of f. I mean, here it's fa. So the area of the pink, it looks pink here. I know, purple, whatever. It's pink in my screen, in my monitor. And this one is fa plus 1, and this one is fa plus 2, meaning the area of the rectangles, etc., etc. So we have that the area, the integral, which is the area bounded by the black graph, is bounded by, let's put it a bit. Okay. The area, which is the integral of f, is bounded by the sum of fn when you start it from a. And on the other hand, that's what you said, let's take the blue color. If we use the rectangles with the heights as the most right point of the segment, we get a rectangle with area a plus 1, and a rectangle with area a plus 2, and a rectangle with area f of a plus 3, and so on and so on. And now these rectangles, each and every one of them, they are beneath the graph of the function. So the area they are bounding is smaller than the area bounded by the graph of f, but what's the difference between the series of the pink rectangles and the series of the areas of the blue rectangles? One little difference. We start the sum in a different point. And as we know from Infi, and it's not right just about series, right about sequences and all other stuff. If we change one finite number of points, specifically only one element, here the sum starts on the right hand, it starts with FA. Here it starts with FA plus 1, and this is the only differences. Both the sums, the pink and the blue one, are converges or are divergent. If one converges, the other is convergent as well, and vice versa. So intuitively speaking, I want to save this. So as a PNG as usual. So just a sec. I'll paste it right away.
Yeah.
Um, I'll explain it just a second. Let's put it 7. 7? 8. Those are big. Okay, so notice that the series from A to infinity of Fn converges if and only if the series of Fn starting at A plus 1 converges. And now, intuitively speaking, if the series converges, then the integral, which is smaller, converges as well. Some sandwich or whatever. And on the other way around, if the integral converges, then the blue series converges, yet again, a sandwich or something. And then, because the blue and the pink are almost the same, the pink converges as well. Formally speaking, we do not have a sandwich rule between integral and the series. Formally speaking, if we assume that the series converges to some number a, then the integral is the limit of the integral from a to b. And we know that when f is positive, the integral itself is an increasing function. F is decreasing, but as long as you move forward, the area you add is becomes greater and greater. You add more and more area. You add less area in each segment, but you're still adding. So looking at the integral, defining this integral, the from a to b, is an increasing function. And if the series converges, the integral is an increasing function, which is bounded, so it does converges as well. And the other way around, when the integral converges to some number a, the series, which by definition is the limit of the partial sums, if you remember from Infi 1. If not, we're going to see, not next week, but the week after next week, we'll talk about series again, probably. Then these partial sums are forming an increasing sequence, and as an increasing and bounded series, it converges. As formally speaking, as I mentioned, one should write in the test itself that f is a non-negative, but if f is negative and decreasing, the theorem still holds because both of the series and the integral are divergent. And if you have, yeah, this goes beyond beneath zero. Okay, so that's the sketch of the proof. Don't know exactly what happened in data structures, but what happens in data structures should stay in data structures. Yeah, that's right. Um, and as I mentioned, I want to say one more thing about the integral test before we are moving on. Any questions about our sketch of proof or the theorem or whatever? Okay, so what did I want to say? Let's note. And actually, by the theorem, you can see, by the proof, by the sketch proof, you can see it. The integral is convergent if and only if the series is convergent. Okay, class.
Can we have a proof by sketch be a proof we can use during the exam?
During the exam, probably not, as I like to say. When you can use sketches and receive some points in the exam, yes, it means that the BA, the study you are doing, is not Argazim. Okay.
Yeah, we talked about this again.
I started to say, we see that while both are convergent or divergent together, the sum is greater than the integral.
Yeah.
So they do not converge to the same number. Okay? Note the integral and the series are both convergent or divergent, but if you want to be more cautious, you can, they not do not necessarily. Ness, that's your island. It's a different Ness. Yeah, like that. It's too much E.
Uh, one less S at another L.
Let's check.
Ne-
No, it's with A, necessarily.
Yeah, I think that it.
Necessarily uh, converge to the same number, to the same limit. Let's have an example. For example, and yet again, it is right now, at least, with our current knowledge, pretty hard to calculate the sum of series. What do we know is to calculate the sum of geometric series. So let's write down the function half to the power of x. The integral is, let's look at it I don't know, from 0 to infinity, for example. Let's write down explicitly in the segment between 0 and infinity. The integral is the integral of half to the power of x, which is the limit where b tends to infinity, the integral from 0 to b of half to the power of x, dx. Now, an exponential integral was one of our immediate integrals. Um, in lecture number one, how do we find the antiderivative? We divide the function by the ln of the base, which is ln half, and we put x is 0 and x is b. We have the limit of half to the power of b minus half to the power of 0 all above ln half. Now, when b goes to infinity, half the power of b goes to 0, and we have 0 minus 1 ln half, which by laws of logarithm is 1 above ln 2. And what about the series? While the series is the sum from 0 to infinity of half to the power of n. As we know, it's 1 above 1 minus half, which is 2. So first of all, it's not the same number. Secondly, as we've seen in the sketch of proof, the series converges to a number greater than the limit of the integral. If you start the series one step forward, you started at n equals 1 in this specific example, you get a sum which is smaller than the integral itself by our sketch of proof. Okay, so it's one important thing to notice. They do not converge to the same number. Not necessarily, because if you take some, I don't know, a constant function which is always 0, so 0, 0 is always 0. Yeah, it's the same limits, but generally speaking, it's not the same limit. Okay. Any questions about our okay. So I want to investigate, explore the connection between series and integrals even more. And if we look back to Infi 1, which was extremely fun, and we talk about what do we know and don't know about series, after the very definition of a series is the limit of the partial sums, what is the first proposition, theorem, whatever you saw with errors? The first one. Before the ratio test, before the nth root test, before the Dirichlet, what was the first one? What? Even before the P-series. I call it the necessary but not sufficient condition for series convergence. If a series is convergent, the AN, the general element of the series, must go to 0. The other way around, we know it's not correct. If AN goes to 0, it doesn't necessarily mean that the series is convergent. But we know that if a series is convergent, then the function must go, then the element must go to 0 when n goes to infinity. That's my question. Does the same applies to integrals? A question. But from a to infinity, okay. Be a convergent proper integral. Does f goes to 0 when x goes to infinity? Now, A little of common sense. By the way, I ask the questions. What the question? What is the answer?
Uh, if you're asking, probably no.
Probably no, of course. Um, but why is that? And what I want to do in the no, the 15 minutes, something like that, that are left, I want to answer you given a counterexample for this basic question, and then discuss what happens when we, on one hand, add conditions. I mean, let's say f is continuous, let's say f is non-negative, let's say f is positive, etc., etc. F is monotone, F has a limit. And on the other hand, if we look at some weaker um, outcomes, I mean, no, okay, not F goes to zero, but can we say at least that F is bounded, for example? Okay, so, but for a first question, let's give the counterexample. Not necessarily, as we seen before, that's how you write necessarily. For example, Um, a number you like?
Well,
Well, first of all, the function sinus x to power 12 does not tends to zero when x goes to infinity. It does not have a limit at all. Um, fx, which is sinus x squared, and goes to infinity when x goes to infinity. But the integral is convergent. We substitute. Once you write it, it's too much t's. Substitute t as x12, substituting whatever, gives us that dt is 12, x bar of 11 dx, which means that dx is dt above 12 x to the power of 11. But right now, if if t is x to the power of 12, then x is t to the power of 1 above 12. So one can write down, instead of x to the power of 11, we can write t to the power of 11 above 12. Yes. What about the boundaries of the integral?
uh, the,
Boundaries? Yeah. As if x is 1, then t, which is x to the power 12, is 1 to the power 12, which is 1. If x, second limit, goes to infinity, then t, which is x power of 12, an environment. T, which is x to the power of 12, goes to infinity as well, right? The x goes to infinity, t goes to infinity as well. And so, what is happening? Your integral or integral substituting our substitution, we get the integral from 1 to infinity, sinus of t multiplied by dt above this nice little 12. Now, be not afraid, child. 12 is just a constant. We can cast it away. Shush, shush, shush. And we have 1 above t to the power of 11 above 12 and multiplied by sinus. Why? Why does this integral converge? We mentioned last Sunday the Dirichlet test. Dirichlet's theorem says that if we have a multiplication of functions, now denote f be the fraction and g, straight g homie, be the sinus, all the condition, we have all we need, all the ingredients for Dirichlet to put up some work. F is decreasing, F goes to 0, F tag is continuous, G is continuous, and G of X, which is the integral of G, is bounded because it's cosinus, as we've already seen in Sunday. So the integral, as promised, is convergent. But the function does not goes to 0. So what was the most basic, yes, concept of series? If the series converges, the general element of series must goes to 0. It doesn't correct. It's not true when it comes to integrals. Now, the next question can be the following one. Okay, what intuitively happens here? The sinus is sometimes positive, sometimes negative. Then somehow the negative parts and the positive parts cancel each other, and we end up with a convergent integral. If we add condition, let f be a non-negative function with a convergent integral. Moreover, let f be a non-negative and continuous function with a convergent integral. Does it necessarily mean that the f goes to 0? Or, yet again, one can find, probably more complicated, but still, one can find a counterexample. Okay, so next question. Following question.
Uh, um, the continuous decreasing positive function can be odd or even. Like, oh, no, it's not.
No, I'm not talking about a symmetric segment. Talk about from A to infinity. A non-negative continuous function in the segment A to infinity with a convergent integral from A to infinity. Does f goes to 0 when x go to infinity? Yet again, by the way I asked the question, what do you think the answer is? No. Hmm. But in order to write down a counterexample, one should be more creative than usual. It's not as simple as sinus, whatever, but I want to show you an example. I want to write it down explicitly with fx is, not just geometrically speaking. And after we do that, we will quickly discuss another following questions. What happens if f is positive, not just non-negative? What happens if I want a differentiable, not just continuous function f? What if I aim to a bounded function and not the one that goes to zero? Probably it's difficult to achieve such result. But maybe if I will be okay with a bounded function. I can prove it, and so on and so on. I need to leave some questions to the test, to the final exam, and right now the answer is no, or formally speaking, not necessarily. The answer is no, not necessarily. So it's necessarily. For another example, for a counter example, we define a function f in every segment from n to n plus 1 for n greater than 2, a natural number. If the function is defined on every segment from 2 to 3, from 3 to 4, from 4 to 5, so it's defined on all the segment from 2 to infinity. And I can define it from 1, but for the numbers to be n, not n minus 1 or something, I want to start it from 2. And how do I do it? First of all, geometrically speaking, okay? Geometrically, let's write it. I don't know. We want function like what I'm going to draw right now. Where is the annotate? Where is the love? Okay, you don't need the y-axis as usually do. And let's write down here it's n, and here it is n plus 1. In every segment, I want the function to do something like that. A triangle, and then to be, let's write more explicitly, a triangle, and then 0. And then you start again to be a triangle, whatever. Now, why do I want triangle and not, let's say, rectangles, which are simpler, I think, simpler shapes? Because if I want a continuous function, I cannot draw it as a rectangle. A rectangle is not a function. I cannot have a such line. I can have some, we call it in Hebrew, stairs, yeah, madrigot, but it won't be continuous. With triangles in every segment, the function will be continuous. Now, what do I want about these triangles? If the function is is built from triangles, the area beneath the function, the integral, is the sum of the areas of the triangles. So I want to have triangles with areas of 1 above n squared, or something like that. So when I talk about the integral, I will have the series of 1 above n squared, and here they are equal. It's not the integral test. I mean, geometrically speaking, the area beneath the function, the blue graph, is the sum of the rectangles. Yes, it goes on the same, on the next segment, n plus 1 to n plus 2. Now, how do I achieve such goal in a triangle with an area of 1 above n squared? We know what the area of triangle is, right? Is the base multiplied by the height divided by 2. So thank you for the yes,
Or
your reassurement. Um, So this point is n and 0 with the y value. And here, let's say we look at n plus 1 above n squared, and the height is 1. And here again, we look at the point of n plus 2 above n squared with y value. What went down to 2? It looks horrible. 0. Now the base is of length 2 above n squared. The height is 1. 1 multiplied by 2 above n squared multiplied by half because it's a triangle area gives us exactly 1 above n squared. And yet again, the n squared is not specifically needed. If it was 1 above n to the power of 3 or 4 or 45, it does the same trick. We have an area beneath the graph, the sum of the areas of the triangles, which gives us a convergence series. Now, let's paste it to the PNG and move on. I want to write down explicitly what f is. Not just geometrically speaking, but fx is, and then write the different cases and see in every one what f should be. And I did it when I teach Infi, I always do it, and we love to ask it in the final exam. Probably not the same question, do we? But as I mentioned, a similar question. What happened if I want a positive function or a differentiable one or whatever? So, want a function like, let's paste it, this. 10 and 8 and whatever. In that way, the area beneath the graph of f is 1 above n squared in n plus 1. So the area in 12 to infinity, which is the integral, oh, what the hell? Okay. From 2 to infinity is the series of 1 above n squared that we know to be convergent. So we have a convergent integral. We know by geometrically speaking, we see that the function f is non-negative. It's always above the x-axis. And it is continuous because it's triangle. We don't jump or have some holes in the function. F is continuous and non-negative, but still the function does not go to 0 when x goes to infinity because we mentioned before, how do we define the limit of function? If all the limits of the sequences go to the same limit. But we have here, if we look at the points n plus 1 above n squared, the value of f there is always 1. It does not go to 0. It doesn't go to 0. So, because f n plus 1 is 0, is 1, which is not 0, even though n plus 1 above n squared, that goes to infinity. So, the function such as that, fx blah blah blah, that actually geometrically speaking is triangles, whatever, whatever, is a counterexample for our question. Function is non-negative, is continuous, and has a convergent integral, yet it does not go to zero when x goes to zero. As I mentioned, I want to write down explicitly, formally, what f is in every segment from n to n plus 1. And then we can move on and discuss quickly and shortly the following questions on the following question. Before we do that, any questions about what I already said? Okay, so let's write down f explicitly. We write, wrong, we write f explicitly. In every segment, the form of n to n plus 1, f is divided backward to three parts. A, a line, straight line, yeah, from the point n0 to the point n plus 1 above n squared and 1. B, a line from the point n plus 1 above n squared plus 1 to the point n plus 2 above n squared and 0. And C is 0. F is 0 from the point n plus 2 above n squared and 0 to the next point n plus 1 and 0. Yet again, we look at the drawing, beautiful drawing. I have the best drawing, etc. Straight line goes up, straight line goes down, and 0. And yet again in the next segment. Now, expect from yourselves, yeah, not what I expect from you, to know how to find a function describing a straight line between 2 points. Don't know if you remember it from high school or whatever, but a straight line, without remembering anything, okay? You need to know that a straight line has the form of ax plus b, right? You know that. So in order to find a and b for case A and A and B for case B, one can put x as n and y as 0, and x as n plus 1 above n squared and y as 1. You get two equations about of A and B, and you find A and B. And do the same here. Now, it works, yeah. But more elegant way to do so is to first find the shipua, is the slope between two slope, the slope of the line, and then put it in the equation. Let's just quick reminder, do a different color. So choose.
Y1 over x2.
Yes, as let's write it down quickly. A line between x1, y1, and x2, y2. Slope is the difference between the y's above difference between the x. And then the line is y is m multiplied by x minus x1 plus y1. You can choose whatever point to be the one and the two, of course. So in our first line, the slope is in the y, we go up 1. In the x's, it's n plus 1 above n squared minus n, which is 1 above n squared. And we end up with n squared. So the function is fx is, it's right now, so we can see it all clear. Fx is the slope, which is n squared, multiplied by x minus 0 plus n. Yeah, I used this point. Always use the point with 0. So we have n squared multiplied by x plus n. This is the first part of the function. One can check if I put n here, do I get 0? The answer is no. So somewhere here I am wrong. Where am I wrong? Where did I go wrong? It's n squared. It's I switched the x and the y. Y is the 0. X is the n, so we have n squared x minus n to the power of 3. And yet again, one can put x is n, y is 0. One can put x is n plus 1 over n squared, y is 1, and see that both are correct. You get a true statement. As far as I can see, yeah. And here, the second part, the slope is similar but not the same. We have 1 minus 0 and minus n plus 2 above n squared, which leaves us with bottom line minus n squared. Comma, so the function is fx is minus n squared using the point of 0 as y, which is minus n squared minus n to the power of 3 minus 2, as far as I can see. Yet again, when one plugs in n plus 1 above n squared, he has minus n. No, something is not right. I'm doing it quickly and I'm failing miserably. It's plus, right? Because minus minus makes a plus. And right now it should be working fine. Yeah. So, in the bottom line, in conclusion, our function, our counter example is fx is is when x goes from n to n plus 1 above n squared, function is first equation we have. Hopefully it wasn't wrong. And when x is between n plus 1 above n squared to n plus 2 above n squared, this is explicit form of the function. I put the spacing here. And for every other point in the segment between n and n plus 1, f is 0. So in the segment 2 to infinity, for every n to n plus 1, we define f in this way. So we eventually have f on all the infinite segment. And this function, as we mentioned, geometrically speaking, has a convergent integral, is continuous, is not negative, and still it doesn't go to zero. Doesn't go to zero. Such a shame. Now, of course, oh, this is of course, I say it out loud. I do not expect you to out of the blue and give me this example. It's a complicated one. It's not the most complicated, most difficult thing in mathematics, no? But it is. What I do expect from you is right now, after we saw this basic concept of examples, looking at per segment and then define some triangle, and we mentioned a rectangle or whatever, um, trapezoid, okay? I can slightly change the question, and then with your knowledge about these kind of examples, try to answer it. Yeah? And that's what I want to say about the quick discussion about the following question. To the following question. Before we do that, any questions about our following question and the example of triangle?
Um,
Yeah.
for n here, do you enter the number or
Every natural number. I
oh
mean, from two. But if you put in one, so one plus two is actually three. Just thinks. But when you start from two, it should be fine. Yes, two, probably. Maybe three? Even three, I don't know. Yes, if you put n is two, you still get x between three and three. And here you get, if you put n2, squared. No, it's two, it's fine because it's squared. Two is fine, yeah. You put n2, it's two and a half, and here's three, two is fine. One causes problems.
so this this function there is less and less triangles, but it will go along, right? Because it's
No, there is, or there are, whatever, an infinite number of triangles. The point is that they become smaller and smaller. The width, yeah, I mean, the height is still the same. It's still one. It's always one, but the width, they become
mm,
narrow and more and more narrow.
sadder and sadder,
Huh?
sadder and sadder.
Narrower, as you say it. I don't know. So now, following question. For example, let's say I want to check if f must be bounded. Yes. Um, following questions. Um, firstly, the same conditions, meaning f is continuous, non-negative, and the integral is convergent, does f does uh, f is bounded. That's not good. Is f bounded, right? Yeah. Does is present simple and is present progressive. Yeah. Here, I don't know where you studied English in high school, but here in Israel, they emphasize all the grammar. I mean, I studied, there is a tense in English, it's called future perfect progressive. I will have been doing. I never used it, and probably every native English speaker never used it. But here in Israel, we studied it. So I know that does is present progressive. Is it present progressive? Is F bounded? What say you? Think about the example we just wrote down. How can I adapt can change it a bit, so the function will not be bounded. But still, be continuous, non-negative with a convergent interval.
Uh,
Look at the,
I mean,
we look together.
we have the red function or whatever.
No, 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 no. Dirichlet is probably negative or something, like the sinus. No, no. Look at this example. How can you change this example in a way that, on one hand, all the conditions are the same, the integral convergent, whatever, whatever, and on the other hand, the function is not bounded anymore?
You make the height dependent on n, and then you make the volume infinitesimal.
The First of all, you're correct, but I say it more precisely. It says if you take the height dependent on n, for example, instead of one, put n. So in every segment, the triangle becomes higher and not bounded. If we shrink the base, correspondingly, if the height is n, let's say the base is of length 2 above n to the power of 3, then the area stays the same. It's 1 above n to the power of 2, and it converges, but the function is not bounded. So, no, with a similar example, a triangle between n to the power of 0, n and 0, n plus 1 above n to the power of 3, and then n plus 2 above n to the power of 3 with 0 again. Rest of the segments, n to the plus 1. We get the same area, the series of 1 above n squared. But now the function is not bounded because the value of f at the points of n plus 1 above n cubed is n, which goes to infinity. And not just 1, as in the first example, but a bit of adaptation, and we get our nice counterexample. Second question, the same conditions, but instead of a continuous function, we have a differentiable one. I mean, a stronger condition. Does these stronger conditions applies that f goes to 0, or at least f bounded? Yet again, the answer is no. But here, writing down the explicit function might be a tough mission. So I want just to explain geometrically how do we do it. Talking about triangles, the function is not differentiable. And why is that? What is the prototype example of a continuous but not differentiable function? Is the absolute value of x. It has a spitz, yes, it has a point where you don't have a tangent line, so you don't have a derivative. And here we can uh, see it in our example as well. The point here, this is a tangle that missed it. This is a tangent line, and this is a tangent line. And the concept of tangent line, the concept of derivative, it's just not defined here. What can men do against such reckless spitzes? We can, and it's a mathematical concept. It's not called not called rounding. It's called smoothing. It's called smoothing. We can look at some more round functions, yeah, that will be differentiable if needs be. Now, defining such function is more complicated. One need to use or some, polynomials that we know that are round and not spitzish. And on the other hand, one can maybe use some exponentials that goes to zero, but acts nicely when it comes to the differentiability and smoothness. Um,
Can you use modulo?
what do you mean by modulo?
Like you have the for everything that is n, then whatever it's a zero, and for that point it's the square root of y plus a modulo x.
What is modulo? Talking
Modulo
about real
itself.
numbers.
No, it's the modulo of x, not modulo of three numbers. So it's just uh, doesn't matter.
Okay, I mean modulo. What do you mean, though?
Because you take um, I can't explain it. Basically, you take out like you know what I'm talking about. It's the square root of y squared plus x squared is the circle.
Yeah.
So instead of doing that, you do from whatever to n, it's zero, and then from n to I don't know how to calculate 1 over n squared for the circle, but for whatever the circle would be, it's the square root of y squared plus the plus x modulo n squared.
As far as I understand, I'm not sure it's going to work because if you look at this function with both of the parts, and you try to define, the derivative in the point where the function breaks, you have different values from each direction, as far as I can imagine it. No, as I mentioned, it's not very, even though we've already seen the example of the um, triangle, it's not very easy. Let's delete the smoothness line. So now um, one can smooth the edges of the triangles, but unlike the first question, which I do expect you to know how to write down the function explicitly because it's basically the same as the explicit example we've already wrote down. Here it's a bit difficult, so I don't feel ashamed if you can write it down explicitly. One can ask GPT if he has a simple solution for that. Ask him, I want a function on the segment from 1 to infinity, whatever, convergent integral, the function is differentiable, the function is not negative, and yet the function does not go to zero. You probably um, to say some nonsense on the first attempts, but if you focus him, maybe they can give you something good. Okay, so for my last question that will be answered by no, I want to show you one question that is answered by yes. One can take the same conditions, but positive instead of negative. But positive instead of negative. Now, using the same no, oh, the answer is no, is f goes to zero. Now the answer is no. I mentioned no, using a similar example, but the function should be lifted, yeah, above the x-axis. So if we talk about drawing, it should look like um, something like that. Yeah, for every segment from n to n squared, we need to write down something as, let's write down a different color. The triangle starts above the x-axis, and then it goes down slowly but surely to the next point. Meaning, for example, we have here the point n with a height, I don't know, let's say 1 above n to the power of 3. And here we have n plus 1 above n to the power of 3 and 1, or n if you want it to be unbounded. And then we have here n plus 2 above n to the power of 3 with the height of 1 above n to the power of 3. And here we are getting down slowly but surely. Let's say the height here is 1 above n plus 1 to the power of 3. So here the function is positive and the function is continuous and the function does not go to 0. But what is the area? The area here is built from three different areas. Yeah, the triangle, the rectangle here, and here it looks like a rectangle, but it's actually a trapezoid because it's not the line, the blue, long blue line isn't actually parallel with the x-axis. It's decreasing slowly, but decreasing. The height starts with 1 above n to the power of 3 and ends with n above with 1 above n plus 1 above 3, which is smaller. Um, what? No, I mean one can calculate specifically the areas here. Now the rectangle here is height above and multiplied by length. It's 1, 3 multiplied by 2 above and 3, which is convergent.
So the upper part goes to zero, like the lower part goes to zero and the triangles are the same as before.
Yes.
Okay.
So it's still because triangles does not go to 0, but it is always above the x-axis. What is the area of the triangle? Its height is 1 minus 1 above and 3, and its base is 2 above and power 3 is multiplied by 2, and this one converges as well because it's of order of n to the power 3. And the area of the trapezoid here, area of trapezoid, um the height is actually the x-axis is 1 minus 2 above and 3 and multiplied by the sum of the bases, which is O of n to the power of 3, and it converges as well. So here, when we discuss writing down the function explicitly, it is possible. It's still straight lines, but it's not a straight line, and 0. It is 3 straight lines. So it's more complicated, but not, but basically the same, not totally different than the basic example we saw, as far as the triangle example is basic. It's, 60. Mm, Using a similar example, instead of a triangle and 0, we look at no, no, lifted triangle and a trapezoid. And let's do the job. Now, we have a minute and a half, and what do I want to finish with? What can we add to the conditions? And then you can say, you know what? Yeah, f goes to 0. Of course, f goes to 0. It doesn't count. So, on the other hand, for all these examples, on the other hand, if the integral of f,
Oh,
want to study infi 2 in English? Why not? Come join us. The algorithm doesn't wait. Int if integral is convergent and f has a limit, f goes to L when x goes to infinity, then L must be 0. For example, that's a condition. If f does have a limit, it must be 0 when the integral converges. Another example, if you know that f is monotonic function and the integral converges, then it must go to 0. So mainly there are conditions on f that makes her goes to 0 when the integral is convergent. But the basic notion of convergence means going to 0 doesn't hold here when it comes to integrals. Okay. Any questions about the fun we did today? So, as I mentioned, next week we start a different subject. I mean, we studied about functions, we studied about sequences and series. So, ask the mathematicians, why shouldn't we combine them? Next week we start to talk about sequences of functions.
oh, no.
Yeah, so much fun.